Okay, so I want to do a couple of examples in videos for Gauss's law applications. The first one I'll talk about is a case of cylindrical symmetry. So just to remind you, we talked in class about three cases in which I can use Gauss's law to directly solve for electric fields. And those three cases are three cases of symmetry. And what you're really looking for, so Gauss's law, this expression is always true. If I have a closed surface and I integrate the electric field dotted the area element of that surface and do it over the entire closed surface, what I get is the charge enclosed over epsilon naught. Okay. Now, again, if it turns out that you can pick a surface in such a way so that the electric field dotted with the normal vector on the surface is everywhere constant on the surface, okay, and that takes a special kind of symmetry for that to be true in the problem, then you have that Gauss's law becomes E dot n times the area of the surface equals Q enclosed, okay, over epsilon naught. Okay, and again, this is only with symmetry can we do this. And again, there's three examples of this kind of symmetry. Symmetry. Okay. All right, so let's consider one of those cases, which is the case of cylindrical symmetry. So if we imagine we have an object, a charged object that has cylindrical symmetry, what we mean by that is the charge that's distributed in space, which normally we can put wherever we like, so it can be a function of any coordinate in space. If that it only depends. Now I have to set up a coordinate system. But let's imagine I set up a coordinate system so that I choose a cylindrical coordinate system, and the only dependence is on the radial coordinate. It's basically symmetric along the z direction. That effectively means it has to be infinitely long, and there's no variation in the theta direction. Okay, so this will work for a cylinder of charge, for example, that is infinitely long. Okay, and the variation in the distribution of charge is only in the radial direction, so there's no variation in theta. So imagine I could have, charge concentrated here and it gets weaker as I go out, but it's like I don't know, what's that, a Twinkie? You've got the good stuff in the middle there, and then you've got the sponge cake around the outside, but it's symmetric. Okay, Twinkies I guess aren't symmetric, but anyway. So what we can do is treat cases like this, where you can arbitrarily distribute charge in with radius, but you can't have, it has to be symmetric in z and theta. Okay, so let's consider a particular case. Let's take a cylinder of radius a. So let's imagine that the radius of the Twinkie I've drawn here is a, and then what we'll do is say that the charge distribution, which is only a function of r, we'll take a complicated one just for fun. We'll say that the charge is mostly distributed at the center of the Twinkie, and then falls off towards the edges. So you can choose a number of functions that will give you that kind of effect, but just for fun, let's say it's half a cosine function. Okay, so this function is only valid between 0 and a. Okay, yeah, that's complicated, right? All right, so what this looks like, if I have rho versus r, it's peaked on the axis and then kind of rolls off towards a. Okay, and we'll assume that this is only valid for r less than a. Okay, for r bigger than a, there's no charge, rho is 0. Okay, so let's find the electric field due to this Twinkie. It's a big Twinkie. All right. So what we will do is use Gauss's law. So let me go back here. So if I look at this cylinder that I've set up, what I do when I apply Gauss's law is I imagine a surface. So if I want to solve for the electric field at that point, this point right there. Okay. What I would do is pick a surface that cuts through that point, and pick a surface that cuts through that point and is everywhere normal to the normal vector is parallel to the electric field, and the electric field is constant. So we know in this particular situation, symmetry tells us that the electric field, let me go here, the electric field of this object, sorry, there we go, the electric field of this object has to point only in the radial direction and can only depend on the radius. Now, we didn't need Gauss's law to tell us that. We knew that last week when we talked about Coulomb's law. We knew by symmetry the field lines coming out of this thing cannot vary with theta, and they can't vary with z, just by symmetry. So if we pick a cylindrical surface that goes around our Twinkie, so here's our Twinkie, here's the point we want to solve for, that's some radius r. What's the electric field there? What we do is we imagine a surface that, a cylindrical surface that includes that point, okay, that surrounds the charge, okay? And it's the area of that surface that is going to show up on the left-hand side. So for this surface, because the electric field always points radially, and is a function only of r, because r is constant on this surface, E dot n hat is constant everywhere on the surface. And so we can pull it out, okay? All right, so let's go consider the electric field calculation. So for r bigger than a, we have a situation where if I pick this cylinder as I've drawn it here, it doesn't matter what radius I pick for that cylinder, the amount of charge enclosed is always the same, because the radius of my imaginary cylinder is outside of the Twinkie, okay? As I change the size of the cylinder, the Q enclosed is always the same. So here Q enclosed is constant, and it's equal to the total charge that's in the Twinkie, okay? So in that case, the electric field, so I can write Gauss's law again. I know it's going to be ER times A, that's the left-hand side, simplified because of symmetry, is going to be Q enclosed, which in this case is Q total, over epsilon naught, sorry. Okay. Now the area of this imaginary cylinder that I've drawn is going to be 2 pi r, that'll give us the circumference of the cylinder, times the length. Of course, the length is infinite here. But it turns out, because I'm telling you that the object is infinitely big and it has a net charge per unit volume, it also has infinite charge, really, okay? What is finite about this object is the charge per unit length, okay? Let me show you where that comes from. So the Q total over epsilon naught. And so now, if I divide through, what I find is that the radial electric field is Q total, and let me do this, over L, okay, divided by 2 pi epsilon naught r, okay? Now this object here, so again, Q total is infinite, L is infinite, but their ratio is not. So the ratio is the charge per unit length, which we call lambda usually. So this is going to be lambda over 2 pi epsilon naught r. Okay. Now we've now solved for the electric field of this object. We know the total charge, and as we talked about last week, we find that it goes like 1 over r. And this is consistent with this argument we made about how the field lines from this object, that again, if you think about your Twinkie going on and on in the z direction forever, it's as if it were a giant wheel, and the field lines are spikes or spokes that come out of it. So the spokes have to go out completely vertically in this plane. So let me draw it up here again just to remind you, we did this in class, but they'll come out straight here. Okay, and they don't spread out if you look at them this way. But if I look from this angle at my Twinkie, what I'll see is that the field lines are spreading in this way, okay, out. And they spread over this circle, okay, rather than over a sphere. And because they spread over a circle, their intensity decreases like 1 over r instead of like 1 over r squared. And that's where this expression comes in. Okay, so it turns out that if you're in any region where there is no charge in a cylindrical symmetric situation, what we would call a vacuum region, perhaps, what I call a vacuum region, the field will always look like 1 over r. Okay. All right. Now, we haven't finished this calculation for r bigger than a because we're not told the total charge per unit length, and so we have to calculate that. So the total charge is going to be the integral over volume, I'll just write it this way, of the charge density. Okay, so the volume element for our cylinder is going to be, if I write it fully, it's a cylindrical volume element. So I'll have r d theta. Okay, that's going to be, let me try to draw my cylinder here to tell you what I'm doing. So if I take a bit of the cylinder here, okay, I want to take this bit of the cylinder, a little cube of it. This side, the bottom side here, has length r d theta, where r is some vector pointing from the center to my little chunk of charge. And then this side of the cube is dr, and this side of the cube is dz. So I have r d theta, dr, dz times my rho, which is only a function of r. Now because rho is only a function of r, I can integrate the theta and z immediately. And what I get is 2 pi for the theta, and L, okay, again, L is infinite, but we're going to leave it as L for now. And now what's left over is an integral of r dr from 0 to a of my function. Let me write it out. Rho cosine of pi over 2 r squared over a squared. Okay? All right, so to integrate that, it turns out we can do some substitutions here. You know what? I think I'll skip the calculus of this and just write down the answer. You can do a substitution, of, a variable substitution here. Oh, let me just do it. If I say y is equal to r squared, then dy is the same as 2r dr, right? So I have both those things here. Here's my r dr, that's a dy, and I can take away a 2 to make it work. And I have a y in my cosine argument. So I can rewrite this integral as pi L integral of 0 now, because y is r squared, I'm going to go from 0 to a squared dy. And I need a rho naught here. And I have a cosine now of pi over 2 y over a squared. Okay, and I know how to integrate that. That's just a cosine. And so when I integrate it, what I'm going to find, is that this is now q tot again, is pi times L times rho naught. Okay, and I end up getting a 2 over pi a squared as I do the integral, times sine, I guess I am going to write it out here, sine of pi y over 2a squared, and that's going to go from 0 to a squared. Okay, and now I can plug everything in, take my limits. The 0 limit's going to give me 0, and what will be left over is the following, that the total charge from this distribution will be 2 rho naught a squared times L. Okay, now of course that's a rho naught and that's a 2. Of course Q total and L are both infinite, but I can define lambda, the average charge per unit length, as Q total over L, and that's just going to be 2 rho naught a squared. Okay, and this is for this very particular distribution. I have to be told what the distribution of charge is in this case. Okay, it's an insulator. Let me try to write that better. It's an insulator, and so I have to tell you where the charges are in the insulator. And so you have to be given the information about the charge distribution, and that leads to this being the total charge per unit length. Okay, so with that, now I can write down my my final answer. That I know E is equal to lambda over 2 pi epsilon r, but I can write it in terms of the givens. And so for r greater than a, I have E r, is 2 rho naught a squared, that's my lambda, over 2 pi epsilon naught r. Okay? All right. So now let's treat the case of r less than a. So for r less than a, now the difference is I'm inside the Twinkie with my imaginary surface. So the amount of charge that I enclose depends on where I am, where my surface sits. Okay, so Q enclosed is not constant. Okay, is not a constant. And so it will depend on where I am as I do the calculation. So my left-hand side of my Gauss's law expression is the same as before. It's just ER times A, and A is going to be 2 pi RL. Okay? But now on the right-hand side, it gets complicated because my Q enclosed is now going to be an integral that, well, it was an integral before, right? I had to do Q total, I had to integrate it, but I integrated it all the way out to A every time because my surface always enclosed everything. But now I'm going to integrate just out to R, okay, of that same integral. So let me put back in, and in fact, well, let me do this. I won't skip a step, okay? So let's put in the integral. So it was 2 pi L. This comes from already simplifying the volume element. 2 pi L rho naught cosine of pi over 2, r squared over a squared, and let's make it r prime. Make it r prime now that we're using our integral variable of integration. There we go. Is r, so let me fix that. So r prime squared, okay, and there's a dr over there that I missed. Let me try to squeeze it in here, dr, okay. So now I just have to do that integral. Oops, somehow I messed up my 2. There we go. And we did the integral already, so we know how to do this integral. I'm just going to write down the answer, which will now depend on radius, okay. So that's going to end up being the following. So this right-hand side will become 2 rho naught over epsilon naught L a squared, okay, times sine of pi r squared over 2a squared. Okay, so that mass there tells me how much charge is enclosed by the Gaussian surface that I'm imagining I'm drawing inside this Twinkie. Okay, all right, so now I can write down the electric field. Okay, and this is again for R less than A here inside the charge distribution. And it becomes the following. I know that the charge per unit length I can write as 2 rho naught a squared, and so I'm going to go ahead and substitute that in here. Well, let me write it twice. I'll just so I don't skip a step. Okay, so I just divide by 2 pi RL, and I get the following over 2 pi epsilon naught R sine of pi over 2 r squared over a squared. Okay, and now I can simplify that again. ER, because I know again that lambda is 2 rho naught a squared. That's the charge per unit length along the cylinder, the total charge per unit length along the cylinder. 2 pi epsilon naught r. So it looks like the line charge field, but it's modified very importantly by this sine function, r squared over a squared. There we go. Okay, and one last thing, let's plot it now. So there's my answer. I'm done. I've solved for the electric field everywhere in space due to my twinking of charge. Kind of hungry for a Twinkie now. I have to go get one. All right. They still make them? I don't know. All right, let's see. So this is the electric field as a function of radius. Now, I know that outside the charge, so at A, it falls off as 1 over r. Okay, so this is going to be my lambda over 2 pi epsilon naught r. Now inside, it turns out, I didn't calculate this for you here, but if the charge, the same amount of charge was distributed uniformly inside, you'll do this in discussion and you'll do it for homework. What you'll find is that the electric field goes like R. So that's for a uniform, the dashed line, let me just, to be clear so I'm not confusing you, the dashed line here in red, that's not necessarily clear, is if the charge were spread uniformly. Okay, so instead of a Twinkie with the goodness in the center and less goodness outside, it's all spread uniformly. If I concentrate the goodness, the charge at the center, it turns out the electric field rises faster, but then falls as you get towards the edge. So this is what the sign, there we go, like that. So this, there's no way for you to intuit that necessarily from the functional form, but this is going to give us, this is the sine pi over 2 r squared over a squared over r. Okay, that's what this function is. So that's our answer. But because we had more charge in the center relative to the edge, it rises fast and then falls off before it gets to the edge. But it has to meet the same point at the edge as the uniform charge distribution does for the same total charge. Okay? All right, I'll stop there.